Perfect. Okay, so we completed our first week of lectures. I wonder whether you have any questions so far. Okay, and if you have any, by the way, I received an email from one of you. I don't remember the name. I will reply. Okay, thanks. I will reply. And an email about providing some more information on biomasses, production energy, and etc. Just 1 second, because I admit one student. Very good. Okay, before continuing the lecture, I just wanted to give you an information. On Thursday, please, the students who are attending physically in the room, bring your PC, because I want to start to make some introduction on calculus, use of open software for making computations regarding numerical modeling. So I think we can dedicate the 2 hours on Thursday. So if you bring your PC, those who are attending in the room, those who are attending remotely, of course, they have the PC. And but if you are attending remotely with a tablet or a mobile, that's fine. But it would be better for those who are attending remotely if you could attend with a PC, because so you can just repeat the things that I will show you and not only looking at what I'm doing. And the purpose of these exercises is to make them interactive, to make them participative and to work together, not just to follow what I am doing. Okay. Now, let me give you just a brief information. We talked about water resources last time, and if you remember, I closed the lecture by showing a picture of a global distribution of rainfall in different seasons. It was an opportunity to discuss orders of magnitude, but it was also an opportunity, if you remember that picture, let me just call it back. I have to share the screen, just 1 second. For the students who are attending remotely, I take the opportunity to have a look at the chat. Okay, good. So let me share the screen.
Professor, sorry, about which software did you want to work with this? RSCDO, because I saw in your...
Can you please state again? I didn't got it. I didn't get it.
You talk about the development, about you using the software, I think.
Yes, yes.
Which software? RSCDO?
I think the best thing to do is to install it together on Thursday. The software, if I talk now about the software, it takes 10 minutes. So I don't think it is an open source. So I think, but it is anyway, it's called R. R, yeah. So it's available, but I think we shouldn't talk about it today, because it takes, just for showing what is about, where is it, etc. It takes about 10 minutes, so I would prefer. Okay, perfect. Let me get back the slide I was referring to just 1 second ago. One minute. I don't understand why it doesn't go in presentation mode, or maybe it's already. No, it's not. Okay, now it's in presentation mode. Just 1 second. Okay, we closed with this picture. So this picture is an opportunity to discuss about order of magnitude. It is also an opportunity to discuss about the global distribution of rainfall, because one thing that we will discuss today, and one thing we are very concerned about, is the fact that water is not evenly distributed. We talked about spatial and temporal variability, and spatial variability is a problem because we cannot move water in space, but it's also not easy to move water in time, to transfer water volumes from 1 month to another. And we will discuss about these shifts and how we can indeed compensate for this even odd distribution. And so it's also an opportunity, but we will discuss again about this to see what are the countries which are more water rich. And I think that it is useful if I just give you an additional information. It is linked somewhere in my website, probably, not probably. It is linked what I'm showing now to you in the next lecture, not the one that we are just looking at in these days. So this this information that I would like to provide to you is a database, a global database of statistics related to food and therefore water for the world's countries. And in order to find it, it is very easy. You have to go to a Google page and just look for Aquastat. Database of the FAO, you see the first link is Aquastat FAO's Global Information System on, let's click on it, on water and food, water and agriculture. So here you see an introduction, and if you look at the database, if you are interested, I just invite you to look at this website independently. This is not something for the exam, it's just something for your education, for integrating your education. It may also be an opportunity to get data that you may use for your thesis, for instance, for making an additional inspection, an additional learning on topics that may be interesting to you, like for a thesis. There are several databases of global information that are coming up, many of them. I'm not really an expert, but you can find, for instance, global information taken by satellites on land cover, vegetation cover, and also regarding water levels, because with satellites you can also get information on water levels in huge surface water bodies. Small rivers, it's a problem because of the resolution of the image that is taken by the satellite. But if you look at huge water bodies like big lakes, you can find information on water levels. Another interesting information that have been used already for about more than 10 years in scientific research is the global database of the gravity force. There are shifts, changes, minor changes in the gravity attraction, in the gravity force over the globe. And these minor changes are given by concentration of mass in the underground. If you have an underground where there is a huge concentration of mass, then the gravity force becomes more powerful. And so if in the underground you have a lot of water, because there are aquifers storing a lot of water, water is heavy, it's a significant mass, and therefore through the measurement of gravity you can get an idea of the distribution of groundwater resources. Actually, you can get an idea of changes, because by comparing changes in gravity, for instance with respect to 10 years ago, and by compensating for other causes for change that we know, we can get an indication about the change of the groundwater volume, which is interesting, because you may know that one of the concerns at the global level is the depletion of groundwater resources. So let's have a quick look at this database. It is very easy to explore it. If you click on databases, and then you can see here, for instance, country statistics. Let's look at it. Again, database. And then finally you get to it. It's a bit slow, but when it will appear, you will see that you can select about several different information. And for instance, there is information on population, and there is information on, you see here, you can select the type of information on the left. For instance, let me show water withdrawal by sector. Let's select all of them. Water withdrawal by sector. Sector means agricultural, industrial, municipal, and total. And then let's focus on Italy. Yeah, please. Do you have any question remotely? Okay, it seems. Okay, thank you very much. Let's wait for it, and then we will get some statistics about water withdrawals for Italy. But you can also select several countries together. You are not forced to select just one. I took Italy just for giving you something that it's impartial, independent. We are in Italy, so I just took the country where we are. As I said, it takes a little bit of time, but it gives you numbers. And also it's possible from here to get maps. I think it is an interesting database. It has been widely used already for scientific research, but still, it may be interesting for you. You see here, there is a table, and it starts from 1988. And then you see the agricultural water withdrawal. So in Italy, you may see that it looks like it is a little bit decreased, the agricultural water withdrawal. This may be a good thing because it may be that the reduced withdrawal is after the introduction of successful policy for water savings. So you shouldn't just conclude that if we take less water for agriculture, it means that we produce less foods. Actually, I think it is more the result after the year 2000 of the introduction of the European Water Framework Directive, which forced a little bit to, not a little bit, really forced the member states to put into practice policies for water savings in agriculture, because of course we are concerned by it, because it's as we know, because we discussed it last week, water withdrawal for agriculture is responsible for 70% of the global water withdrawals. And then there is the industrial water withdrawal. You see that Italy, it is also decreased. And again, maybe water savings. Municipal, in fact, I was not expecting a decrease. You see that there is a slight increase, because in this case, to save water is more complicated, because in agriculture, the losses are higher with respect to the piped water supply systems. And then there is total water withdrawal. And again, you see overall a decrease, which is a good thing. And then irrigation water requirement, if you look at them, they are not decreased in the past 15 years, which means that indeed food production is not decreased. And then there are some other statistics. And this is interesting because this is just for one country, but if you look at a global distribution, of course, you can get an information of how water resources withdrawal, water resources use, has been evolved from about 40 years ago, 35 years ago to today. As I said, this is just an example. There are several databases available for getting information. And for instance, if you're interested in climate, you may look at the Copernicus system of the UA, of the European Union, and it's of the EU, sorry. And this is a database which provides information on climate, and both historical information and future projections. It's not easy to use. This one, Aquastat, is very easy. You have seen that you click, and then you get the data. And the Copernicus system, it's a little bit more complicated. You need to make some programming. You need to know some programming language, and especially and specifically Python to use it. And this is another demonstration that, knowing computer languages may be useful in many applications. Actually, the Copernicus system is not much used. The Aquastat database has been widely used for scientific research. The Copernicus data system, not so much. And I think the reason is that getting the data is not really easy. And but I can say that I'm not a Python programmer. I don't know Python at all. But in one full day of work, I was able to download the data I was interested in from the Copernicus system. Okay, now this is just a nice way to start. And now let's continue. And let's continue with our discussion on climate, because if you want to become a water resources expert, you have to start from climate, of course, and then from climate you have to put hydrology into it. Hydrology is the science of the water cycle. Climate is not just enough. This is one thing that I'm trying to promote. It's one thing I am really passionate of. We have today motivation and a tendency to look at climate and think that climate is just equivalent to water resources. Actually, climate is the provider of water resources, but it is really what is really determining the overall availability, the overall distribution of water resources is the combination between three systems: climate, water cycle, and humans. And you have to put these three things together. Otherwise, if we just account for climate, what we get is a partial picture. It's not really the end of the story. It's just the beginning. But indeed, we have to start from climate. And a nice way of getting an idea of the climate of the world is the Köppen climate classification. It was introduced recently. In my website, there are more details. Just, I'm showing you a map in the next one, in the next slide. Just keep in mind what the legend here. And basically, in the figure that you will see with the next slide, just keep in mind that the climates labeled with the letter A are tropical. Letter B is dry, letter C is mild mid-latitude, letter D is cold mid-latitude, and E is polar. So let's just look at the next figure. So tropical is A, so it's the blue colors. Let me just turn off the light here. Okay. Blue color is tropical, lot of water, okay? And now there is also the B is dry, no water. And so look at the red spots, also orange ones. These are the countries suffering from lack of water, dry climate. And then there is the green. The green is good conditions because it's mild temperate and it's very good for agriculture. It's a belt that where there are favorable conditions for food production. And then there is we said the D is it's cold climate. So when you see where you see the dark blues in the north, it's cold climate. It's not, there is a lot of water, but you know, it's not really favorable for food production. And then there is the polar region, which you already know. So just to give an idea, you find a Wikipedia page with the Köppen climate classification. It was introduced not many years ago, and I think it is a really nice way of having a picture, a global picture of water distribution. Okay, now let's have a more detailed look. This is taken again by the FAO database Aquastat. It's 2015, so you can find these maps updated. There has been not much changes from 2015. Also, when you talk about water distribution in general, there have been not much changes from 50 years ago because climate change has affected a lot of global warming, so there are increases in temperature. About the distribution of water resources, it's not really what happened so far is not really putting in evidence a massive change. And there are some concerns about the possibility that the extremes have changed a little bit, like very extreme rainfall. Actually, the data don't speak for that. So the data that we have available for rainfall don't confirm that there has been a major increase in extreme rainfall. And if we look at the distribution, the changes are even more subtle. So, I mean, if a picture of 2015 is perfect, is perfect to give an idea also of the distribution today. What is this? It's total renewable water resources per inhabitant. And basically, if you remember, here dark blue means a lot of water, light blue means less water. If you remember, the distribution of climate is more or less mirroring what you see here, okay? And then renewable water resources withdrawn. And here you get a proportion of renewable water resources. So you get a picture that on the one hand says something that you may expect. Where there is more water, then people tend to get more water. So basically, if you remember the United States, overall, if you forget the spots, the dry spots in California, in the West, overall they have a lot of water. There is a lot of water there. And this is the reason why people moved in end of 17th century, moved from Europe to United States because it was very favorable for agriculture. And but they also tend to get a lot of water because, of course, a huge proportion of their renewable water resources. Renewable means something that you can, of course, get without the concern of the water getting depleted. So it means surface water, it means groundwater with fast recharge time, okay? A second thing that you see here is that, of course, countries where there is less water, they tend to get a lot of it. And a lot of it in percentage terms, in proportion. And this is, of course, something that you may expect. On the other hand, it is a little bit concerning because, you know, a lack of water means an obstacle to sustainable development. And therefore, where you see that a huge proportion of water is taken where there is not much of it, this is a bit of a concern, of course. And water withdrawal per inhabitant. And you see a picture that it doesn't say much more with respect to what we saw so far, but it's interesting to see that there are indeed countries where people tend to use a lot of water. And when we say water withdrawal per inhabitant, we mean all the water withdrawals, not just for civil use, but also for industrial use. But still, I mean, it's, of course, there are countries where we tend to use a lot of water, countries that use less of it. Now, proportion of total water withdrawal for agriculture. Again, it's a picture that doesn't say much more. And what I just would like to say is that if you consider the global average is 70%. So it means that 70% of the water that we take from natural resources is used for agriculture. But if you take the average of individual countries, so you get for each country the percentage of water that is used for agriculture, and you take the average, not a weighted average. So United States is averaged with Cyprus, the same weight, okay? And then you get to a percentage, a global percentage of 60%, 59 actually. What does this mean? It means that there are countries that use a lot of water for agriculture, and more than 70%, and countries that use less water. And here you see this clear disparity, okay? And these are percentages, which means that it's not actual volumes, it's percentage, proportion of total water withdrawn for agriculture. So it means that if I get just a few, very small volume of water, but all of it is for agriculture, is 100%. Even if the country is very small and the volume of water that is taken is small. But it is interesting to see in this picture that indeed the distribution of water that is used for agriculture is not homogeneous, as we can expect. Okay, and then now let me talk about the distribution in time, which is seasonality, basically. If we look at climate, climate is what I said before, the provider of water, and climate is seasonal. And therefore, in the same place, we talked so far about spatial distribution. Now, let's focus on a single place. In any single place of the world, there is seasonality. In some countries, it's very, how to say, flattened, the seasonality. It's very reduced. In other countries, there is a lot of seasonality. What is seasonality? It is the distribution along the year. It's the intra-year distribution of climate statistics. In this case, we are concerned by rainfall, by precipitation, let me say. Precipitation is the water that we get from the atmosphere. It may be in liquid form, and then we say rainfall. It may be also in the form of snow, and then we use the term precipitation to mean the total of it. Now, it's clear that where you have a strong seasonality, there is a more fluctuating distribution of precipitation over time. And here you see in this figure, which refers to Europe, some examples of river flow regimes. What do I mean with the river flow regime? I mean the distribution along the year, the intra-year distribution of water flow in a river. Just to remind you what is flow. I go over the river, I look at it, and ideally I measure the volume of water that passes along the river per unit time. This is flow. Okay, the unit is like cubic meters per second or liters per second. Remember that 1 cubic meter is 1,000 liters. I think we already discussed this. So when I talk about river flow, keep in mind, because this is something that I may ask at the exam, what is river flow? And it may seem trivial. It is something that you study usually in hydraulics. Just keep in mind that you measure in a specific location of a river, you measure the volume of water that passes per unit time. Let's forget about how we can measure it. Okay, let's suppose that we can measure it. Okay, and actually it is not easy to measure it, and there are several technical indications in order to make the measure unique. Because as I defined it, you may have some doubt, like, what does it mean, volume of water that passes through the river? Ideally, I tell you, go over a bridge, look down, and just think at the amount of water that is passing beneath your feet per unit time. Okay, and let's forget about how it's measured. This is another thing, this is another order of magnitude that you should become expert of. It's more difficult than rainfall. Okay, but you should have an idea. If you want to become a water specialist, you should have an idea of the order of magnitude of river flow. Like, think at your country, the most important river. Do you know the average flow of the river during the year? Probably the answer is no. I can tell you when I completed, maybe that when I completed my degree, I knew the average flow of the Po River. But if one asked me what is the minimum flow, an order of magnitude of the minimum, or what is an order of magnitude of the maximum, I couldn't reply at that time. So just try to get an idea of this information. You don't need to know this for every river in the world, of course, but just to get an idea. So again, think at your country, get the most important river, and then go on Wikipedia, look at the statistics. You find them. And for the Po River, I can tell you the average flow is about 1,500 cubic meters per second, average flow, okay? If one asked you what is the minimum for the Po River, of course the minimum varies from here to here, but an order of magnitude for the minimum is 600 cubic meters per second. Don't forget the units, okay? Don't forget. And this is something I may ask at the exam, like what is the unit for flow? Okay, and it is a tricky question, because sometimes we think that there are things that we know, like rainfall, river flow, we know what is that. But if we are asked to define it, then we get in trouble. And given that you are, almost all of you are engineers, or let's say will be engineers for sure, and okay, I know that there are some students in the room probably studying natural sciences, but still, you are attending a lecture in engineering, you have to be rigorous with definitions, with technical issues, because this is what makes your expertise unique, okay, with respect to other kind of expertises. So again, what is depicted in this picture in the small rectangles is the distribution per each month any of these small pictures, count 12 bars. Each bar is for the average monthly flow. And then you can see for different rivers in Europe, the distribution of the average flow along the year. When you see big changes, this is a bit of a problem. These are all huge rivers, so all of them don't get dry during certain periods. They are not intermittent. Get these terms, okay? Intermittent means that sometimes you go there and there is no water. All of them are not intermittent. Some of them are very flat. The pictures are very flat. And this is something that, okay, maybe that in some of the cases there is not much water, but still the fact that it's flat, it's reassuring because it means that, okay, maybe that there is not much water, but that water I can always find. When I have a distribution that is very peaky in certain months, and in other months there is much less water, then I need storage. There is a question, yes?
The term basin irrigation. So can you define how much they play an important role in flow regime?
I am sorry because the mask, and you should repeat it, then I repeat your question. Please say again.
The term basin or the basin irrigation. So can you define the basin irrigation, how plays an important role in flow regime?
So you mean, you talked about environmental flow in the end of your question and irrigation. So your question is about, can you talk about irrigation requirements and environmental flow?
I'm talking about the flow regime, how to the construction to we get the water to the irrigation. So the basins we are talking about, we are making about in order to get more flow and continuously flowing.
Okay, I understand. So basically, I repeat the question, I get close to the microphone. The question is related to irrigation, and the question is also related on how we make sure that there is enough water for irrigation and preserve the environmental flow, okay? It is okay, I'm sorry if I have problems in understanding. Yeah, you need a reservoir. If you want to compensate the odd distribution of water along the year, you need a reservoir. And if there is a distribution that is not much variable, then maybe that you can get water for irrigation through a run of the river withdrawal, which means that you go directly to the river, you put pumps there, and you get the water from the river. The problem, we will discuss about this, the problem is preserving the environmental flow, because a reservoir can help because you store the water and then you release the water when you need it, and also you release the water in order to maintain an environmental flow. But still, the reservoir is a bit criticized as a solution because it is an alteration of the natural flow regime. So there are several reservations about, yeah, please.
Sometimes we have the upper basin and lower basin. So can you differentiate it? What is really the term exists?
The
upper basin and the lower
basin.
Yeah,
I got it, yeah.
So can you differentiate it? Means can you make a difference? Can you tell the difference between them?
Yeah, okay. The upper basin is the part of the basin that usually catches the water. So it is in the mountain typically, and in the mountains you have more rainfall because of the orographic effects. So the mountain part, the upper part of the basin, is the part that catches the water. Typically it doesn't use it because in the upper part, you don't, given that you have a lot of rainfall and there is not much agriculture because it's hilly, it's steep, typically people just take the water from rainfall and they have enough, so they don't use it. But in the upper part of the basin, it is the part where water is stored, where reservoirs are built. And then there is the lower part. The lower part, it's more prone to agriculture, and it's the part that needs more water, and therefore it is the part of the basin where people often push for storing water. but water is not stored in the lower part, it's stored in the upper part, because also for making an artificial reservoir, you need mountains usually. You need deep valleys. So this is one reason of the conflict, because of course people living in the upper part of the basin, they take the damage from the reservoir because they lose some land, and also they are concerned by the flood that may come from a reservoir, from a dam, even if just for dam breaking, but not only dam breaking. When you have a regulation of river flow, then it may turn out in an increase of the flood risk. So in the upper part of the basin, usually people are not happy with the construction of the reservoir. Downstream, in the lower part, instead, they often push for water. And therefore, there is some friction. And also there is to say that sometimes upper part and lower part are in different countries. So, of course, it is difficult for people living in a downstream country that to push for a dam that should be located in another country. I hope that I answered your question, basically. Okay, thank you.
Sorry, in this figure, the unit of river flow is per month?
Yeah, it should be, it should be, I think it is written somewhere, but in any case, this is mean monthly flow, long-term mean monthly flow. It is, I don't remember the period on which the average is computed, but I think it is something like 50 years. It means that you have a measurement of river flow for 50 years, and then you take for each month the average. Is it clear? Okay, very good. The distribution of river flow in general mirrors the distribution of precipitation. There might be some shifts due to snow, due to the presence of snow and glaciers. So if you go in the Alps, you have precipitation during winter and river flow during summer, of course. And there might be some shifts that are operated by the basin, by the catchment, because part of the water is stored in the underground in the form of groundwater and is released later on. So actually the catchment, it's a filter of precipitation. A filter means that it's smoothing the distribution, okay? If the catchment is not storing water, is very, very impervious, we say, no infiltration, then the distribution of river flow is mirroring the distribution of precipitation. If there is storage in the underground or in a dam, in an artificial reservoir, then the distribution is smoothed. Any question about this? But still, it's a problem to compensate for this uneven distribution in space and time. It's a big question mark. Okay, now, how can we solve the problems? So what is our problem? Our problem is water scarcity. When we talk about water resources system, if there is a lot of water, it's not a problem. We wouldn't study water resources systems in engineering if had we a lot of plenty of water available. It is very easy. I mean, if you live just close by to a river with clean water, actually you just need a pump to bring the water into the house, and that's it. It's not really an engineering problem. It becomes an engineering problem when there is partial or constant in time water scarcity. What is water scarcity? It means that the demands for water is higher or comparable to water availability. And now there is a mismatch, okay? And then it becomes an engineering problem. And of course, there are several different solutions. If you have a mismatch between demand and availability, you have, in principle, and very trivially, two possible solutions: reduce demands or increase availability, okay? The traditional solution was increasing availability. This is the traditional solution that we follow. And how can we do that? we have to increase the water supply. This was the traditional solution, the historical solution, which was used by the Romans already. They built aqueducts in order to move water for hundreds of miles. And they didn't build artificial reservoirs, but they used small reservoirs into the city or into their houses in order to, in a way, to compensate for the time shifts, for the uneven time distribution. There are many other examples, historical examples. By the way, if you are interested in the history of water resources system, there is a link in my website which brings to a paper written by some colleagues that provides an interesting historical overview. You may say, what is the benefit of studying the history? Actually, the benefit is really important. If you want to become, again, a water expert, I suggest that you also study a little bit the history of water resources, because there are many problems that we think that they are new. Actually, they are not. Like climate change is not a new problem. There were several civilizations in the past that suffered from climate change, and their solutions are still, in some cases, still important today, still actual. And I mentioned the story of the aqueduct of Bologna. I think this is a clear demonstration of something that the Romans built, which is still used today. And to provide some examples of important interventions that were put in place in order to move water, I can mention the Ismailia Canal, built along the Suez Canal, was built in the 17th century to bring fresh water from the Lake Timsah to the city of Suez. And there are several other examples that may be made which were conceived in order to increase water supply, increase water availability. So the demands were compensated by increasing the water supply. Now, these traditional solutions are the reason of concern today. Why? Because of their environmental impact. And if you think about how can we increase water supply, we can build aqueducts, we can build reservoirs, artificial reservoirs, and all of these interventions have a huge environmental impact and a societal impact. And therefore, there are concerns. But this solution was widely applied historically. And if you think at the artificial reservoir, they got their golden age last century. In the 20th century, a lot of dams were built in the Western world and also part in Asia. I think, give me 1 second, there is an interesting link in my website, and just 1 second. Let me go back. I don't think it's here, so let me go back here. Because one thing that I miss when I show the slides is to draw your attention on the links, which are interesting and also give the opportunity to make some interesting discussion. This is the list of the largest dams in the world. And this is not the list of the tallest ones. It's the list of the largest dams in terms of volume. And the list is not ranked in terms of reservoir volumes. And I think that probably we could get this link here. And I think they are listed here in terms of reservoir volume. Yes. So basically, you can see here an interesting list, even if I don't see, let me just see. Okay, there is the Three Gorges here, which is not okay. So actually, the Lake Kariba reservoir probably is the largest one in terms of volume. Okay, the list is very long, but it's not exhaustive because there are several dams that are not huge volumes, but still they are very widespread. And in Italy, for instance, Italy is very mountainous, and therefore there has been a proliferation of dams. And so you can understand that indeed the environmental impact is relevant. What are the reasons of concern? The reason is deprivation of river flow downstream. I just give a incomplete list, because if you think of alteration of the natural environment, there are a lot of issues related to that, which is ecology, and also the stability of the slopes, of the hill slopes, because of course, when you build an artificial reservoir, there is also a risk associated to it, a risk of instability, a risk of collapse, and there is the risk of instability for both storing water and reducing the infiltration of water downstream. It may cause instabilities. And also there is occupation of land. These huge reservoirs occupy a lot of land. There is also the concern of altering not only the temporal distribution, but also the spatial distribution of water use. Because of course, if you build a dam upstream, then the water that was originally used downstream may be not available anymore. This is the case of the Nile River, for instance, where there is a sequence of dams that have been built, and now they are filling up the Millennium Dam upstream, which may deprivate the downstream water availability, and therefore they may have problems in filling the Aswan Dam, which is downstream. I mean, there is a lot of implication in that, and therefore recently, about mid of the past century, people realized the effect of the environmental impact. They realized what was the result, and the result were dry rivers, groundwater decreasing in volume, etc. And therefore, a movement arose together along with the movement that was promoting sustainability, sustainable use of resources. A movement arose that pushed for identifying alternative solutions, environmentally friendly solution, and this was associated to the creation of the Green Parties that gave fundamental support to this new wave of ideas. So what is the alternative? This is something interesting, the cost of water supply, and it is on my website. So you can see that taking water, of course, implies a cost, and the cost is very high for desalination. And you can see the costs associated to where the width of the bar means the variability of the costs. So you can see the costs associated to each water source. But I was saying, what is the alternative solution? The alternative solution is reducing the demand. So these are the issues that we will talk about during this course. So on the one hand, increasing water resources availability. On the other hand, decreasing the demand, and decreasing also the losses. This is another important issue. I think I already mentioned to you that the leakages, losses, are reduced for piped water supply system with respect to the water supply systems that use canals. So open channel flow for moving water is more environmentally friendly on the one end, because of course we are not much concerned by looking at canals that are full of water. even if they are artificial, they look environmentally friendly, and they are indeed environmentally friendly because they preserve evaporation, they give some infiltration in the underground, and therefore, I mean, from an environmental point of view, with respect to a piped system, they are more environmentally friendly. On the other hand, when we talk about open channel flow for moving water, let me call them natural canals with no concrete on the bottom and on the sides, we talk about water loss of about 50%. So it means that if we take water from a dam or from a river in the mountains, and then we take a certain amount X, only half of it reaches the final destination. And the rest is lost for evaporation or infiltration. And this originates a huge debate, an interesting debate, because some people say, okay, but it's not water, it's not lost water, because evaporation means that I preserve the natural environment. Infiltration is the same thing. I give some water to the water table, to the underground water bodies. But still, I mean, from the point of view of an engineer, if we design a water supply system for a specific task, I think it must work well. It must work for the purpose. So if we design a water supply system that wastes, losses half of the water, okay. I mean, one may say it's not lost. It's like when you go to buy something and you pay twice for it with respect to another vendor. It's not money lost. It goes in the pockets of the person to which, where you bought the good for twice the price. But still, it's not a good management. So if I am an engineer and I am asked to provide a consultancy for designing a water supply system, I need to identify a target and reach the target. Otherwise, it's not a good design, because the water losses are unintended consequences, which, I mean, I am really not sure that they are beneficial. I'm really not sure that water that infiltrates through a canal then goes to replenish the underground water body, which may, in the future, serve another purpose. It may be water that goes somewhere else and originates a perturbation of the system. So it's not really, this is something that I have to frequently discuss, like when we propose to substitute a canal with a piped water supply system, we are often told, yeah, but the canal is nicer, but the canal gives water to the underground. And my reply is always, look, when you have to reach a target, I mean, you cannot say that to justify the fact that you didn't reach the target, you cannot say that nothing apparently wrong happens because you didn't reach the target. The target was not reached, and for an engineer, this is a problem. I mean, it's clear, if I have to be at work at 9 a.m., if I am there at 10 a.m., I may always say, okay, but I didn't die. It's time that I lived, I enjoyed. Yeah, but you didn't reach your target. So, I mean, it's the fact that a water supply system loses 50% of water is something really concerning, because it means that we get twice the amount of water from the river. It means that we have twice the environmental impact, and this is not a good thing. So, of course, the solutions to reduce the water losses are not easy, because it's not because we are not good engineers that we lose 50% of water. It's because the solutions to the problem are not trivial solutions. And even if you think of a piped water supply system like the water supply system in Bologna, losses are at least 30%, at least. In most of the cases, it's a little bit more. Okay, so reducing losses. This is a solution that it's popular today. Keep in mind that when you have a problem to solve, nowadays there is an important task related to it, which is to convince the stakeholders that the solution that you devised is a good one. This is something that was not so important in the past, because in the past we adopted typically a top-down approach. The managers decided, and people had to accept the decision. Today it's different. Today there is a more, we'll discuss about this later, bottom-up approach. Means that we are required to consult with the people first and to find a solution by establishing a common dialogue, a participated dialogue. And therefore, for an engineer, it becomes today very important to be able to convince, as I said, that the solution that we are devising is the right one. Now, if you propose to build a dam, this is something that usually is convincing. For people that are suffering from lack of water, if you show a picture of a huge lake, a huge dam, people feel relieved. If you say, I am reducing losses, they don't see the solution. They don't see the additional water. And I talk for my personal experience. It's really tough to convince people that distributed solutions, not clearly visible solutions, are effective. And so keep in mind that the water demand control regulation needs to be really well conceived. And when you go and explain what you propose, you have to be very rigorous, very good motivations, no doubts, ability to answer questions, because these people ask questions, and you have to be ready to reply, so figure out in anticipation what kind of questions you could get. And this means getting information, it means studying, and you have to be very, very capable of providing answers, convincing answers. Okay. There are other solutions for reducing the water demands, and other solutions that I think you know quite well, like closing the tap, and so making information campaigns in order to educate people to save water, and farmers. Another interesting solution is weather forecasting for farmers, and irrigation planning, and precise irrigation. It's not discussed here, but this is a topical issue today. And I think we have to reach the target of providing to the plants just the water they need, not more. Because if you give, by the way, more water, it could be dangerous, let's say, it may be not efficient also for the food production. Once that a plant has got enough water, that's it. If you give more, if you are passionate of gardening or vegetable gardening, you know that if you give too much water, in some cases, the plants die. So precise irrigation needs to be informed by weather forecasting and by a careful assessment of the behavior of the soil, the behavior of the plant. So for a given forecasting of the weather, for a given plant, for a given type of soil, there are informed systems that may tell farmers, look, tomorrow you have to give this amount of water to each plant. And then if you have drip irrigation, so a system that is able to bring to each plant individual amount of water, first of all, you don't irrigate the surface that doesn't need to be irrigated. And you give precisely the amount of water that each plant needs. Of course, we need investments to do that, because these forecasting systems, these learned systems that make the analysis of the soil, they require a lot of information. This is not something that can be done by an individual farmer. This is something that has to be organized at the societal level. And then we may need investment by the single farmers, because drip irrigation is typically an investment that is made by each individual person. But then it pays back. It pays back because they spend less money for water, and they get an agricultural production that is more qualified. And also more productive. I'm talking about agriculture for obvious reasons, because we know 70% of the global consumption is related to it. And also pricing. Pricing has been proved to be very effective. There are a lot of discussions because, of course, we cannot raise the price of water too much. Water is fundamental, is essential for the life, so we cannot. We have to give access to water to everybody, including the farmers, of course. On the other hand, there is a clear demonstration, a lot of scientific studies, that within orchestrated strategy that keeps anyway the price at a regulated level to make water accessible. Within this well-governed system, if you increase the price of water for given services, you reduce the use, you reduce the demand without provoking a big discomfort. You know, we know that every one of us has the tendency, sometimes we tend to use too much water because it's also pleasure. I mean, there is nothing nice like going into a river and enjoying fresh water. And also when you open the tap, it's something that is really enjoyable. On the other hand, we don't have to exaggerate, so a good pricing may be a good motivation for induce some savings. Another thing that we will discuss is reducing the impact of extremes. And let's talk about droughts, for instance. If we make our water resources systems resilient to drought, meaning that they can cope with drought, we can save water. We can save water because think of a reservoir. You know, if you're able to, in a way, to predict the droughts, to set up emergency management, in a way, if you are able to set up a strategy to cope with unexpected events, this implies that the size of your reservoir is reduced. If you don't have an idea of the impact of an event, if you don't have an idea of what we can efficiently do to cope with a drought, then of course the solution is to make a huge reservoir. In this case, in a way, you increase your safety factor. But if you can predict the extremes, then you can reduce the safety factor. Or this is the language of engineering. So when you have several unknowns, increase the safety factor. It's typical. Like, for instance, when you have to build a levee to avoid a flood, it's not a matter for this subject, but let me make this example. If you don't have an idea of the max river level, you build a very high levee. And this is a problem because it's impactful. It costs a lot. You oversize your solution. Oversizing, it means environmental impact, whatever, because in engineering, whatever we do has an environmental impact. And if you oversize, it's a problem. If you can predict the impact of extreme, then you can reduce your safety factor. The environmental impact is reduced, and the water use is reduced. Okay, let me just talk about this slide. In water resources, there has been an increasing popularity of the bottom-up approach, not only water resources, also in risk management in general. And let me just make a comparison. Let me talk about the top-down approach first, which means a top-down decision. And basically, we have managers here who take their decision, and then people are affected by the decision in a positive or negative way. I mean, it is also a system that worked really well in the past, so it's not only negative. And the top-down has an advantage. The advantage is that discussing with people is difficult. And in some cases, managers identify the solution but cannot convince the people that the solution is good. And therefore, what is the risk today, where there is an increasing popularity of a participatory approach, participated approach? The risk is that you don't do anything because you have a problem, like, water resources, water scarcity. You have a problem. What is the solution? The solution may be a reservoir, but some people say, no, I don't like it because I am concerned by the risk of flood. I am concerned by the changes in the river flow regime. Today, building a reservoir is almost impossible. I mean, in Italy, building additional reservoirs is almost impossible. And then a second solution may be pricing, reducing the demands. And people say, no, I don't like it because increasing pricing is not good for a democratic approach because we have to be equitable. And therefore, if we increase pricing, basically we impact people based on their richness, on their money availability. And therefore, I don't like it. And therefore, very often, we have discussions that go on for tens of years, and at the end, we don't do anything. I can make several examples of recent managements where we were not able to conclude anything. One interesting example is Florence. You may know that Florence in 1966 suffered from a huge flood. It was 55 years ago. Good. The situation in Florence now is precisely the same as in 1966. Same thing. So if another storm like that one happens, Florence is flooded. And in these 50 years, they discussed a lot of possible solutions, and only minor intervention, very minor ones, were adopted. Because, of course, some people say we need a reservoir upstream. No reservoir for the environmental impact. Okay, so let's forget it. We need to reserve floodplains to store water in case there is a flood. Then we can breach the levee upstream and store water in a retention basin. So this is the technical term. We need retention basins, and people say no, we don't like it because we need that land, because that land is needed for urbanization, is needed for producing food. So they rejected also the idea of the retention basin. Fine. So let's increase the size of the existing reservoirs. No, because it becomes dangerous. So let's increase the height of the levees. No, because the city is historical and the tourism, etc. We cannot do that. And then they said, okay, let's make a map of Florence with the inundated areas so people get prepared. And the map was produced, but then it has to be withdrawn because people said, no, absolutely, because my house is located there and the price of my house goes down if it is classified like a house that can be inundated. And they had to withdraw the maps. So nothing has been done in 50 years. So this is the risk today. So I mean, the top-down approach had instead some advantages because you are convinced of a decision as an engineer, you take it and then you prove to people with the facts that it works. After a while, if it works, you can prove to people that. And this was adopted in the past in several cases. But on the other hand, it's not really democratic, it's not participatory. So basically now the bottom-up approach is more popular, which means that you have to start from people, you consult with people, you explore all the possibilities, all the alternatives, and here it talks about floods, but you can substitute inundation routes, and so you explore all the alternatives and whatever. Let me just check what is this beep. I think there is a student that needs to be admitted. Just 1 second. No, okay. I don't think there is anything. Okay, very good. So basically, you start from the bottom and you get to the top and you identify at the end the solution that is agreed by stakeholders. I really believe this is the way to follow today, but beware of the problems. And the most important problem is that you run the risk of doing nothing. And this is also the case for climate change. You know the story today, and people complaining because nothing has been done by politicians so far, even after the Paris Agreement, etc. But why? Because anything you may think of is a problem, and some people don't agree with. So this is basically the problem. And so if you want to reduce the emissions, okay, let's go for electric cars, but only rich people can take them. And you can't oblige people to change the car all of a sudden. Let's go for solar energy. Solar energy, it's impacting visually the environment. Wind energy, a lot of noise, and also the environment, the landscape is impacted. So in certain lands, you cannot do that. So discussion, endless discussion, and at the end of the story, I mean, we are doing something, but not really much. But keep in mind that this is something that it's coming up, and we just need a good way of managing it. And we need to rethink the role of engineering, not only as a science, as a discipline that is in charge of identifying solutions, but also as a discipline that needs to communicate with people. It's a discipline that has to take in different consideration the environment and our relationship with the environment. I mean, in the past, it was not really a concern. People built dams without caring too much of the consequences. Now, you have to make an assessment that is really refined. Okay, and now, so far we just talked. Now, let's focus on some technical issues. I mean, we already talked about some technical issues. I talked about orders of magnitude. I introduced the definition of river flow. But these were just, it was just the beginning. Now, we need to go into the technical thing. And in this premise that I made so far, what are, in your opinion, the issues? I mean, what I discussed, like increasing water supply, reducing demands, there are technical issues behind. And the role of the engineer is precisely to clarify, to provide the technical information. In water resources, the technical information is given by data. And the first question that we have to address, which may seem trivial to you, is how much water do I need? And let's postpone this. Second issue, how much water I have available. Estimating water resources availability is the first issue, which is by far very complicated. It's not like designing a building, a structure of a building, where I have what is the technical information, is the loads, for instance, and then the type of soil and the resistance of the material, but the loads are our technical information. When we design a building, okay, there are uncertainties in the loads, because when I talk about wind load, seismic load, snow load, there are uncertainties. But by far, when I deal with water resources, the uncertainties are much higher, much, much higher. And even to a trivial question like how much water is available, I don't have an answer. And this is something that is not easy to communicate. I am doing a consultancy for the water supply agency here in Bologna, ERA, and they take a lot of water from the underground. They want to know how much water is beneath our feet. And when I say it's not possible to answer to this question, they can't believe it. Because today we live in an era where we think that we have data for everything. So we have data for weather forecasting, we have data from satellites to explore the world. We have a lot of Earth information today. But actually, to a basic question like, what is the average river flow for an unknown river, or what is the volume of water that is stored in the underground, we don't have an answer. And then we are trying to get into this problem, to get why we don't have the answers. And so my next lecture, which is the first technical one, will be precisely related to water resources assessment, which means that I have to estimate how much water is available from a given source. There are several water sources, rivers, lakes, the sea through desalination, groundwater. How much water is available in a water body? In a given water body I am interested in. How much water can I take without undermining the environment, without causing an irreversible environmental impact, without crossing a tipping point? Tipping point means a flip. Okay? These are the questions for us, very fascinating ones. Questions where there are opportunities for saying, for giving your voice, for giving your contributions. Because when a question is unsolved, then it's an opportunity. You understand? Okay, before I move into that, let me just check on the web page, because I finished this lecture. Let me go to my website. I finished this lecture, which is sustainable management of water resources. You see that the next one is assessing water resources availability. Let me just go back to the lecture that I just finished to see if there are some links that are interesting to see. Just 1 second. Here there are some links that are curious, like the autonomous buildings. Let me see if it works again. Yeah, there are some experiences today of autonomous buildings. So building designed to be operated independently from infrastructural support services, like water resources, for instance. And these are buildings where all the water that is used is recycled. By the way, it's possible to recycle water also from the sewer systems and get drinkable water. Now, today we have emerging technologies for that. In Europe, it's still not allowed, but there are some countries in the world where it's used. It is costly and it takes a lot of energy, but this is becoming a reality in the future. So what is called circular water resources management is becoming a reality. Now it is quite common also in Europe to reuse water from buildings, but for flushing the toilets, so not drinkable uses, or reuse water for irrigating the garden. So there is an increasing, for instance, frequency of systems that collect water from the roofs, store the water into tanks, and use it to irrigate gardens. And this is also useful because we reduce the flow in the sewer systems. And we reduce the amount of water that has to be treated in the sewer system at the end of the sewer systems. So there are a lot of savings associated to that. The problem is the cost again, because a water tank, it's some money, and also for the maintenance, because it's not really a huge expense to build it, because usually when you build a building, also you have also the garden, and it's not a huge expense to dig enough room for in the garden for a water tank. The problem is the maintenance, because if it's not maintained, then the quality of the water is poor. Even for irrigating the garden, it becomes poor, and therefore has to be maintained, cleaned very frequently, and this is a bit costly. But there are a lot of initiative in that sense. Keep in mind that the landscape is really evolving fast, and therefore I am giving to you some information, but really if you become an expert in these tools, you need to stay updated. Okay, so let me close this and let me just see if there is some other things that Also, there is a link on the Wikipedia page for green politics. This is another interesting discussion. And it's technical, it's not political. So, I mean, the interest that I have in the green politics is technical. It is nice to see what is the history of this movement that provided a lot of benefits and some exaggeration. But at the end of the story, it becomes really technical, because the green politics also brought some kind of distrust in engineering, and this is currently a big problem. So today, a big problem that we have is indeed the distrust in engineering, and not only in engineering, I would say also in science, but in engineering there is really, I think, it is really a topical issue. And it is something that is impacting you because, you know, when you have to convince people, there are several people that come at the assemblies, at the meetings with a preconception that engineering is something that it's really bad because it's impacting the environment. And I think knowing the history is interesting. It is technically interesting. Whatever is the opinion that one may have, I think it is something that has to be known. Okay. Here there is something related to aquifers, but we can discuss this later, because now we are talking about assessing water resources availability, and we start with surface water resources. Surface water resources are relatively easy. It's still a problem, but relatively easy. Groundwater resources is a nightmare. And by the way, here you have a definition for river discharge, which is a synonym for river flow. You see the definition, the volumetric flow rate. It is precisely the definition that I gave half an hour ago. It's the volumetric flow rate that flows through a given cross-section of the river at a given time. There is one thing that I didn't define here, cross-section. When I said, let's forget about the details, the flow is the amount of water that flows beneath your feet when you are on a bridge. Actually, we should make reference, and I said, at a given location. I shouldn't say location, I should say cross-section. I think it is intuitive what cross-section means, but still, if you are missing the terminology, when you read in my web pages and you see a term that you absolutely don't know, just make a rapid check on Google and get the definition for it. This is my suggestion, because my web pages are very, very, to the point. So what is written there, they are not redundant for an engineer. What is written there, if there is a term that you have no clue about it, just turn on a bulb in your brain and just say, okay, let's try to get some more, okay? So cross-section, I don't want to provide these definitions because many of you already know what a cross-section is. River cross-section, if you don't know, just go on Wikipedia and you find it. Okay, I think we can go to the next one, and we can talk about assessing water resources availability. I think that probably it's better if I make the break now. I am 3 minutes in advance, but I think it's better if we start next hour. Any question? Don't be shy, because sometimes it's not easy to interact. My English is not perfect, and some of you, most of us, are not native speakers, and the mask is making things more complicated. But don't be shy, and if we don't understand each other, we solve the problem. It would be more of a problem if we just avoided to interact because we are concerned of understanding reciprocally.
Sorry.
Yeah.
Do we have any rules or any instructions that how much we impact to the environment? I mean, when we build the dam, for example, we are instruction, we don't do this. We have to allow, for example, a minimum flow to the downstream.
Yeah. So the question is, do we have any rule and instruction to assess the environmental impact of an intervention? So my answer is, in some cases, yes, and we will discuss some of these cases. Like for the specific example that you made, we build a dam. How much water do we have to release for giving the environmental flow downstream, or minimum flow requirement? It depends on the country, but usually you have legislation that tells you, depending on the size of the dam and depending on the river regime, what is the environmental flow that you have to release. So this is typically an easy question. So environmental flow is typically an easy question. Then keep in mind that in some countries, for some of the interventions, you are required to make an evaluation of the environmental impact. In Italian, we call it valutazione di impatto ambientale. Literal translation is evaluation of environmental impact, which means that it's a quite demanding assessment of all the possible impacts of an intervention. And for instance, for a dam, it's not only environmental flow, it's also the risk of flood, it's also the deprivation of groundwater bodies downstream. And some of these issues are not easy to estimate, and you don't have specific instructions. So the result was, according to the Italian experience, that in some cases these assessments of environmental impact are descriptive and not really exhaustive in terms of estimating what will be going on. And so the answer is partial. I mean, there are some issues that are regulated by legislations or guidelines. They are quite easy to follow, like environmental flow. Other issues, which also there are several unknowns. So my answer to your question is, for some issues, yes, we have instructions, we have guidelines. For other issues, we have to devise something. Okay, other questions? Okay, let's meet again at 11. Thank you very much. Can you please close the door? Thank you very much. Some more words on next Thursday. I said exercises. These exercises are not compulsory, meaning that you may also, when I tell you in advance that I will dedicate time to exercises, you may also decide to skip the lecture. And it's not something that would impact your performance at the exam, because the exercises are not a matter for the exam. I will not ask at the exam any question related to exercises. Exercises have the main purpose of increasing your experience with the numerical computation and computer programming. Also, they have the purpose of providing some examples which increase your expertise, your ability to deal with water resources problems and technical issues. So my suggestion for you is to make an effort to attend them, even if not strictly required for passing the exam. I already mentioned to you that your target is not to pass the exam, but your target is to become an expert in water resources and water resources systems. And I think exercises are really an interesting step. Also, the lecture usually it's entertaining. It's not boring. It's quite exciting because you have an opportunity to really get involved and interact with each other and with me. So my suggestion is to attend them, but on the other hand, I want to be clear and give to you the options to take the best decisions, because of course you are not attending only the subject, you are attending also, you have other commitments. Okay, so on Thursday it will be 2 hours completely dedicated to that. Okay, so let's try to get into a more technical discussion. And before I start, I just want to make a very quick poll in the room. It's enough. And the number of students in the room is more or less the same as the number of students connected remotely. Do you know already what are flow duration curves? So just raise your hand if the term flow duration curve tells something to you. Sorry? Hydrograph, yes, hydrograph, but it's not the same as flow duration curve. So I want to make sure that I'm not providing any information that most of you already know. So I don't, yeah, you know what is a flow duration curve, yes, others, you, perfect. And can I ask you, what is your, where did you study flow duration curves? It is during your bachelor or another course here? Bachelor. Okay. It's
flood and drought with Professor Elena.
Okay, so Professor Elena Todd. So who is attending flood and droughts with Professor Elena Todd? Okay. And is she explaining in detail what is a flow duration curve, how to estimate it? Okay. Anyway, I'm trying to make an effort to avoid repeating too many concepts. And so I think it is always problematic because some of you already know some things and others, your background is different, of course. But I'm trying just to be very focused. So So I will try to be, I'm not saying quick, because quick is a bit reductive, but I will try to be quite efficient in lecturing. If you experience any problem, like you don't understand something, I am running too fast, just let me know, even individually, if you don't want to raise your hand in the room, okay? Okay, so why it's a problem to estimate water resources availability? It's a problem because very often we don't have enough information. So it looks like this is strange. Water is one of the elements that we know better. I mean, if you think about your experience of humanity, but in particular your experience, there are some elements that we know really well, like fire, water, air, forests. And why? Because, of course, they are essential for our life, and therefore it's an element that water, I mean, we have been in touch with water forever. And it is strange then that I'm saying that we don't know much about water, but actually it's true. I mean, we know water, we know how to use water, we know why we need water, but when we think about the technical issues related to how water gets into our house, how water gets into the river, which is completely natural, and we try to think about our knowledge of these processes, then I think you may realize that you don't know much. Of course, we go to a river, we see water, but if you think about the path that this water followed, or some more technical questions like, when did this water rain? You go over a river and you see water. When did this water rain? This is a question for which we don't have an answer. Or how much water is flowing into the river? It is something that we don't know. So this is the problem. The problem is the lack of knowledge, which is related also to the lack of information. So, of course, I talked about river flow. Had we available measurements of river flow, it wouldn't be a problem to estimate the river flow. If I go over the river and there is a monitor showing to me what is the river flow in that precise time interval, then it's not a problem. But actually, we don't have these measurements, and the lack of measurements implies lack of knowledge. So this is why estimating water resources availability, it's an issue, because for some rivers we have data, we have measurements, for some others we don't. Let's forget about how river flow is measured, as I said. Just keep in mind that it's not possible to measure it directly. It's not like measuring rainfall. You put a tank outside during a rainy day. At the end of the day, you go there and you measure the depth of rainfall. This is very easy. River flow is defined, as I said, as the volume of water per unit time that passes through a cross-section of a river, and how to measure it. It is relatively easy from a tap. You open the tap and you put a tank under the tap and you measure the time required to fill the tank. In a river, you can't do that. You can't go there and catch all the water that passes and measure the time that is needed to fill a given capacity. You can't do that. There are ways, anyway, to measure river flow. Just keep in mind that very often we use the water level. So we measure the water level, which is not the same as the river flow, but then we have some empirical relationship to convert the water level into river flow. So if we have the measurements of river flow, then that's easy. I talked to you about the Po River, and I said the average flow is about 1,600 cubic meters per second. How do I know that? Because there are measurements on the Po River, and because it's an important river, and therefore we have observations. But where we don't have observations, this is an issue. So we can just first split the problem in two categories, in two subcategories. The problem of estimating water resources availability can be split originally in two broad categories: surface water, groundwater. We are talking about surface water. Okay, let's split the problem again let's focus on the problem of surface water availability for rivers, and let's split it again in two categories: presence of data, absence of data. And let's start with the easiest situation then, assessing surface water resources availability for a river for which we have data. This is very easy. Still, we need to discuss a little bit how to do, and then we will discuss how to solve the problem when we have no data for a river. Okay, very good. And first, let me say that there are several methods to estimate water resources availability. And but if we focus on data, presence of data, we have data of river flow, then the method is essentially one, which is the estimation of the flow duration curve. Okay. You can get by intuition that when you have data, it's quite easy. I mean, why it's easy? Because, of course, if I know that from the Po River now it's flowing 2,000 cubic meters per second, they are flowing, then it means that I have potentially that flow available for withdrawal. So if we have data information, again, the problem is simple, but still it's we need to understand how to study the temporal distribution. Because, of course, if we have data, we know that in any case, it's not constant, the river flow. So I cannot say on the Po River I always have 1,600 cubic meters per second, which is the average. Because there is variability, there are up and downs. And therefore, if the average is 16 cubic meters per second, it means that in certain days I have less, in other days I have more. So I have to define this temporal distribution. I don't have anything to define related to spatial distribution because I'm referring to a location, to a river cross section, okay? So space is fixed. We are not talking now about distribution of water in space. Space is fixed. It's a river, and more than that, it's a location along the river. It's a river cross section. So space is not a problem. But we still have time variability. So even if we have data, you understand that you can do that, but still how to study this time variability. Because I need also to know not only the average, I need to know these up and downs and when they happen. And if they happen, the ups, when I need water, I am happy. If the downs happen when I need water, I am unhappy. And typically, this is the case. Because we are talking of something, a natural process. When it rains, I have a lot of water into the river, but I don't need water to irrigate because it's raining. Okay? So typically, we have less water available in surface water when we need it. Why this? Be careful. Try to put your mind into the process. Why this happens? I already gave an explanation. I already said, when it rains, I don't need water. But you may think that there is a delay between rain and river flow. You may think that there is a delay. So it's not so obvious what I said. It's not so obvious that when it rains, I have water into the river. There are some rivers where there is a long delay. I made the example of the alpine rivers. I get precipitation during winter and I have water during summer. But in any case, keep in mind that for surface water, the delay time between rainfall and river flow is reduced. It doesn't exist a river for which you get rain 10 years ago and the corresponding flow today. It doesn't exist something like that. I'm always talking about the majority of the flow, okay? It's clear that in a river, potentially, you may have some water, some drops that rained 10 years ago. But if I look at the majority of the river flow, if I look at the massive part of it, it doesn't exist a river with a so long delay. Surface water usually reacts to precipitation within a reduced time. It may be some season, but not more than that. I made the example of the alpine rivers. Okay, it may happen that they respond to precipitation after 6 months, but not more than that. The story is completely different from groundwater. Groundwater may have a delay time of 1,000 years. It may happen that you take water from a well and that water rained 1,000 years ago. It may happen because it's very slow. Surface water is quite fast. So try to get your mind into the processes and keep in mind one thing. When you are dealing with something that is natural and you don't, you have unknowns, and water cycle is something for which we have unknowns, keep in mind that the first thing that you have to do is to figure out in your mind how the process works. This is what you have to do when dealing with water. There is a famous saying attributed to Leonardo who said, when you deal with water, you first have to use reasoning and then experience. Or let me say, it is the opposite. You have to first use experience, which means reasoning, and then the theory. He said, Leonardo, try to use experience before the theory. I say something a little bit different. Try to get a conceptual idea of how it works, the process, and then you take care of traducing in numbers, which means that you need a theory and a model. But first, try to figure out. So, I mean, we have this problem of studying the distribution of the river flow, which is similar to that of precipitation, with some possible delays, but not so huge delays. So our problem now is to estimate this temporal distribution based on data. And it's clear that we need a method, okay? So if you figure out the process, you go over your river, you have data again, and you can, even without looking at the data, figure out that there is a temporal distribution. You can figure out the variability. Is the variability really huge or is limited? And then you can figure out what are the months where you have more water and the months where you have less water. And then you get the data and you have to find a method to quantify this distribution. What is our problem? Our problem is to know how much water and when we have. Okay? Because typically, what is our task? Is to design a water resource system which has to be sustainable. And therefore, of course, if we didn't know anything, what should we do? We should oversize it. If we have several unknowns, we can oversize it. But it's a problem to oversize it because it costs more, environmental impact, and also it is less efficient. When you use something oversized in water resources, it's less efficient. So the solution is to get information and try to understand what is the optimal size of the pipes or of a pump if we need one. And I mean, if you have to size a pipe, as I said, you cannot oversize it because it is costly and less efficient. You cannot undersize it, because if you undersize it, it means that you are not using all the resources available. You are making a suboptimal use of resources. Let's suppose that you have a huge demand. If you cover only part of that demand, while you could cover more by your water supply system, it's not efficient. You have to try to address the demand with the most efficient solution by avoiding undersizing and oversizing. Okay, so how can we analyze this information? And I think we can, I already discussed about this. So let's start from the data. And the data are river flow data. And let's start from a graphical perspective. Let's start from a graph. The graph of river flow along time. Here there is written stream flow. It's a synonym of river discharge or river flow, stream flow. They are synonyms. Okay. Okay, stream flow, cubic meters per second, for instance, or liters per second. In technical, okay, the international systems prescribes the use of cubic meters per second as a unit for flow. Sometimes we use technically liters per second. Why? Because when the numbers are very small, when the river is very small, we prefer to avoid digits. So we prefer to avoid to say this small pipe has a flow of 0.0005 cubic meters per second. We say 5 liters per second, okay? So the graph of stream flow over time is called hydrograph. Hydrograph. Very good. The hydrograph is very easy. You get numbers, observations. Let's suppose, for instance, a daily time scale. Also get familiar with this technical detail. When you get observations, you have to ask yourself or the data provider some questions or metadata. Metadata means specifications for the data. For river flow, I would ask where. So location along the river, cross river section, where. I would ask the time scale. These observations are daily, hourly, minutes, weeks, months. There are several different time scales. Usually the river flow historically was measured at course time scale, daily or 10 days or monthly. Why? Because it is complicated to measure the river flow. Even if you measure the water level, it's not easy. And therefore, the resolution, time scale or time resolution of the data was coarse. Today, we have the possibility with remote sensing to measure at the time scale of hours or minutes. Let's assume, for making our discussion more specific, that we have daily flows available. Okay, so the hydrograph is depicting daily flows. Now, the hydrograph is very easy to draw. You get your time series, another technical term. When you get data expressed as a function of time, typically in environmental sciences, we call it time series. In our case, if we draw a graph of the time series of the river flow along time, we call it hydrograph. Perfect. It's very easy to draw this graph. We get the time series and we plot it in Excel, for instance. Okay, very good. And then we get the hydrograph, which already gives a very good information. I mean, if I look at numbers, it's not easy to extract the information. The hydrograph already says something really interesting, but from a technical point of view, in order to emphasize how much water we have available and for how long, it's better to get another representation of the hydrograph, which is called flow duration curve. How it's defined? Please remember this definition, okay? This is a question that occurs very frequently, and I don't know why students have some problems in remembering it. And the definition is on the screen. The flow duration curve depicts the percentage of time, also called duration, over a given observation period, during which a given stream flow is equaled or exceeded. I repeat, percentage of time or duration over a given observation period. The observation period may be January 1st, 2000, December 31st, 2010, 10 years. Okay, let's refer to an ideal period of 10 years. We have daily data for 10 years, 3,650 plus something numbers. Okay? Now, for this observation period, I want to know the percentage of time, duration, over this given observation period, during which a given stream flow is equaled or exceeded. Good. Now, how to compute it? It's very easy. Look at the hydrograph, and let's fix a stream flow during which a given stream flow. So let's give a stream flow, okay? Then we change it. But now let's give it a stream flow. Let's get stream flow here, the lower one, okay? This one that you see on the screen in correspondence of the blue lines. Okay, this stream flow is given, and you can draw an horizontal line which is intersecting, is crossing the hydrograph. Okay, is crossing the hydrograph. Now, if you get the length of the segments crossed within the hydrograph by the given horizontal line of the given stream flow, you get here two blue segments, B and C. And this, what is their length? Their length is the number of days during which the given stream flow was equaled or exceeded. If you look at the picture, you get that clear. Okay, during the segment B, the given stream flow, let's call it stream flow B, it's a stream flow star, let's say, was equaled or exceeded by the blue segment B plus the blue segment C. Because during these two segments, I had a flow that was, look at the hydrograph, higher or equal. Good. Now, if I take the length in percentage term of B plus C, this is the duration of the stream flow star. Okay, length in percentage terms. What does this mean? If B plus C is 1 year and the observation period is 10 years, the percentage is 10%, okay? Now let's fix another stream flow 2 stars, the higher one, which is crossing only the first wave of the hydrograph, and the length of the segment is A. Given that the stream flow is higher, follow my reasoning, given that the stream flow is higher, I expect that the duration is lower. Okay, and the higher the stream flow, the lowest the duration. Because if you look at the definition, you can understand that. And therefore, I can put in the flow duration curve the corresponding duration in percentage term as A. If you look at the flow duration curve on the right, you see that indeed duration is decreasing for increasing river flow. Question here, please.
I just want to make it more clear for myself.
Yeah.
The length of the A in hydrograph is equal to the length of A in duration graph?
The length of the hydrograph is long. Let's say the length of B and C. You have to divide it by the length of the hydrograph. Did I answer your questions? Okay. Please state it again.
No, let's talk about A.
A.
Because B, C is more complicated.
Okay, A, okay.
A is, for example, for 2-3 years.
Yes.
Okay. I want to see in the duration graph is also 2-3 years or no?
No, in percentage terms.
Oh,
in percentage terms.
It means to 20-30%.
Yes, so if it is 3 years and your full observation period is 10 years, it's 30%. But your question is relevant because sometimes the duration is expressed in let's say, in units, not in percentage. So what you may also say, and you may read on some books, that the duration of A is 3 years. But I think that if we adopt this view, you cannot compare. It depends the duration on the duration of the observation period. So it's better to refer to percentage terms. Okay?
Yes.
Yeah, no problem. Another question, please.
So I have two questions. For being more clear, is the follow duration curve is to make more good perspective of the hydrograph?
Yes.
It is for that, and because we want to know the maximum power rate and also the base one, so we know the duration, and not just to make it more clear the hydrograph, we draw the follow duration. Is this right?
Yes. The question is the purpose of the flow duration curve to make clearer with respect to the hydrograph how long we have some water available? Yes, the answer is yes. Keep in mind that it's just a different representation of the data. And if you gain something, you may understand that you lose something. Indeed, the flow duration curve is just saying how long you have some water available. It doesn't tell you when. The hydrograph tells you when. For instance, if you look at the left picture, then you know that, I don't know, this may be summer. In summer, you have minimum level. The flow duration curve tells you how long you have water available, but not when. In designing water resource systems, this is, let's say, for civil use, it's the relevant information that we need. Also for hydropower production. For irrigation, the flow duration curve alone is not enough because you also need to know the season. The flow duration curve loses this kind of information, but it gives an important information, which is how long. Okay, and if you think about hydropower production, how long is an important information because it is related to the amount of energy that you produce. Second question.
And thank you. And for the second one, the integral of both curves, I think, should be the same, and the volume of the follows, yes.
Yeah.
The area of the under the graphs for both is equal.
Yes, this is a very good question. I meaning that it means that if one question like this it is asked, I realize that you students got the concept because actually you are correct. The area below the two curves is the same, and what is the area? It's the volume of water during the observation period. So the area below the hydrograph, it's water per unit time integrated over time. So it's the volume of water. And the same for the flow duration curve. The same. Of course, if you express the flow duration curve in percentage terms, then you have to make a transformation of the units. But it's the same volume. Yes. Good question. Other questions?
That's why we expect that when the flow is very high, it is for a less period of time because it doesn't rain too much for a long period of time. Because we are looking at the volume, so we are looking at liters, meter cubes.
Yes, correct. Basically, the question was, this is why when you have a higher flow, you expect it for a shorter duration, because it's the same information that you get from the hydrograph. Yes, the area below the high flows is reduced for both of them. Yes, of course, correct, correct. Okay, very good. Now, I think that the concept is clear, and I mean, for the purpose of designing, of finding the design flow of a water supply system, the flow duration curve is very useful. And also it is very useful in order to give a graphical representation. Why? A graphical representation is more useful in some situations, because it is a very significant aid, a very significant support in communication. So when you communicate, as I said, communication is for us a challenge. Graphical tools are very useful because they are more effective in delivering an information. So what I want to give you an example. Let's look at the flow duration curve, and let's consider what we just discussed. The area below the curve is the volume, okay? And let's suppose that we decide the design flow for an hydropower plant. And let's suppose that the design flow is very high, okay, close to the maximum. Then the corresponding duration is low. And the area below the curve, below the design flow, I'm sorry that I cannot draw on the blackboard, because otherwise who is following from home, it's a bit of a problem to look at, but maybe that I can try. Let me just 1 second, because I think it was a nice example what I was saying. Okay, I think from home you should now be able to see the blackboard. Very good. And let me try to draw here a flow duration curve. Let me just draw it, and then let's check whether. Let me just write the river flow Q here and time and the duration D here. Yeah, it's okay. And let's suppose that the flow duration curve is from 0% to 100%. Let me change it. Okay. And let's suppose that it is like this, okay? Very good. Now, let's suppose that we get this design flow Q star. The corresponding duration is here. Let's call it D star. Very good. Now, I can identify an area here. What is this? This is the water that is used by my water resources system, whatever it is, hydropower, water supply, at full design flow. This is the volume of water that is taken by the system at full design flow. So you see that the water is a bit reduced. The volume is a bit reduced. Okay. Of course, the system may work also at lower flow. So the volume that is taken by the system actually is higher than that. But the remaining volume is taken with the system not working at full design flow. Okay? Very good. This is important, especially when you produce hydropower. Hydropower production, when it works at the design flow, is very efficient. When it works at a lower flow, it's less efficient. Okay. Now, of course, here you see that if I take another design flow, Q double star, I think you have a blue chalk here. Now, what is the volume? The volume of water that is taken at full design flow is something like this. D double star. And let me just this is higher than the previous one. So I get more volume of water at the full design flow, but the flow is lower. So this means that if it's an hydropower production, I produce more energy, but the peak energy is lower. So it depends on the purpose, but the flow duration curve, you see that it gives you an essential information. If you look at the area beneath the curve, it gives you an essential information. Yeah, questions, please. Okay, first and then second and then third. First.
If you can repeat the last point about the peak.
Yes, because here the volume of water that you take is higher, but the peak flow is lower. And of course, it depends on your design purpose. You may be interested in getting more volume of water. I mean, I'm always talking about water taken at the system working at the design flow, okay? If you accept that the system works, is oversized, it works with a lower flow, you can get more water. But if I'm focusing on the water that I get when I'm working at the design flow, here the volume is higher, but the peak flow is lower. Your question?
Professor, we choose this data for estimated RDM or something like this. It's not related to the risk of the flow. I want to be clear for me. We choose this data for estimated storage we can have in our dams. Because of this, that part is lower than the Q stars. That's right? That's a good.
Yes, I mean, I got your first part of the question. This is not related to flood analysis. It's related to water resources availability, okay? And why this is not related to flood analysis? Because floods occur very infrequently. Water resources availability, we are talking of something that is available every day. So what is the side effect of this? To monitor phenomena that are less frequent, very rare, you need long period of duration, long observation period. And therefore, you cannot study floods with a time span of 10 years, an observation period of 10 years. Water resources availability, 10 years is fine. I don't understand the second part of your question.
The second part is that we are calculating the volume of our water in the period of the time. It means that, for example, if you want to design a dam, the maximum value of the storage is exactly the maximum part of our analysis of the data. For example, the blue one. Is that true? Or
yes, but in this case, I am analyzing the river in natural conditions. When you talk about designing a dam, the reasoning is a bit more complicated because the dam, this gives to you a picture of water resources availability and the percentage of time during which water resources is available. Then, if you realize that you don't have enough water available for a sufficient time, then the solution is storage. Okay, did I answer your question? Okay, and it is usually not used for designing dams. The hydrograph, yes, you can use it for designing a dam, but it's a bit more complicated, the analysis, because you have to compare the hydrograph with the demands. And then when there is a mismatch between hydrograph and demands, this is indicating the storage that you need. There was another question.
In the graph, sir, we have three type of colors.
Yeah.
Three type of colors: blue, green, and red. I think so. So is there any logic behind it, or just we have to make the curve?
You mean in the graph? What kind of graph? What is
In the slides, sir.
Okay, just 1 second. And let me just check the slide. I'm not putting, no, there is not any logic. It's just to make a difference between the whole duration, which is in green, and the duration of the higher flows that is in blue. And okay, there is one, before I want to conclude by saying one final thing. When I made this discussion, I referred only to the water volume when the system is working at the design flow. Let me just redraw this figure by telling you one more thing, and then we can stop here for today. Okay, let's suppose that this is the first graph that I made, okay? So this is what I highlighted here. It's the volume, the area, which means the volume of water taken when the system is operating at the design flow. If I want to get an estimate of the total volume of water that is taken by the system, even when working at lower flow, I have to add this part here. But this second area that I am highlighting is representing the volume that is taken with the system working at a lower flow with respect to the design flow. Okay? So basically, you may say, it's convenient that I increase my design flow so I can get more peaks and I'm not losing anything in terms of water, of volume of water. But if you do like that, you are oversizing. It means that the majority of your volume is taken with operating conditions that are not ideal. So you need more energy, or you spend, you take less energy, which is the same. Second, it's true that you can cover the peaks, but your system is really oversized, which means that it costs more. Let's suppose now that I refer to a lower design flow, okay? A lower design flow. And then, now I draw in blue this QW double star. The volume of water that I'm taking is the area whose perimeter is now in blue. It's this area. So you see that the volume is indeed lower, the volume that I take. I'm losing something because I'm not covering the peak, but the system is less expensive. So it may be more convenient because I save in maintenance, I save in construction costs, I save in management costs, I lose some water, but it may be more convenient. So you see that the flow duration curve allows you to make a cost-benefit analysis. 2 questions, and then we close. Yeah.
In addition to duration, which parameters have a more effect on the structural changes?
You mean changes? What kind of changes? So
any kind of the changes. There was this volume, there was this flowing and kind of things.
So you mean that? You mean also environmental changes like climate change or?
Yes.
I think if you look at the change in a flow duration curve over time, you get a picture of the changes in water resources availability over time. And this may be useful because it tells you also how your system works during time. It may be that at the beginning it was working in an ideal condition, and then during time it becomes less sustainable. So if you look at changes over time of the flow duration curve, you get an idea of what? You get an idea of the changes in percentage of time when during which you have some water flow available. I'm not sure if I replied to your question, but okay.
Yes, okay.
Yeah, another question.
Is this graph unique for the specific hydrograph or is unique for specific river for doing our project or doing our
To estimate the flow duration curve, you need to refer to a river location, and then you need data. So I make reference to a certain location with a given time series, a given hydrograph. So if you take a different hydrograph, you get a different flow duration curve. And then there is the question of representativity. I mean, if your observation period is 10 years long and you change the observation period, you move forward or backward, it doesn't change much because with a length of 10 years, it's representative. If you take an hydrograph that is only 1 year, from 1 year to another year, you get...
what is time period most common for the district? It depends on the risk of projects?
It depends on?
The risk of projects, for example.
You mean the duration?
Doing a hydropower plant, how long hydrograph is accepted to export in the power duration? Okay,
I think first, you asked what is the optimal duration of the observation period. Okay, as I said before, the indication that I give, for estimating floods, you need 100 years. For estimating water resources availability, 10 years is fine. But it depends on the river. This is just an order of magnitude, okay? Yeah.
If the duration is maybe 10 years or 20 years, maybe, is it possible to prediction for the 50 years by using this prediction?
Oh, okay, so you mean the duration of the observation period. If it is 10 years long, can I make a prediction for the next 10 years? Okay, first of all, as I said to your colleague, the answer depends on the type of the river. And keep in mind that the more the variability of a process and the longer you need of information. Okay, this is a rule of thumb. If you have a process that is like constant, you just need one observation, you know that it's constant, and that's fine. If you know that the process is going up and down, but really a lot up and down, then you need a long duration, okay? And so when I said 10 years, I said like an ideal situation. Let's say that normally with 10 years I am fine. There are some rivers for which 1 year is fine, is enough, 2 years, let's say. And then there are rivers where you need a lot more. Okay, that's it. And making predictions. Okay, first of all, making prediction is not easy, especially when it is regarding the future, okay? So, and I mean, you have to first think, to first evaluate, assess whether the conditions will change, are expected to change in the next 10 years. And of course, you may think that today we are expected that things are changing very rapidly for climate change, environmental changes, etc. But you are an engineer, you need numbers. So you need a quantitative assessment. So you cannot trust the media. You have to try to understand whether you see in the near future, during the lifetime of your project, you can get enough information on relevant changes. So I would say, for instance, I make an example. If I had to make a prediction for the flow duration curve of the Po River for the next, let's say in 2040, I would take the current one and say, this is it. Okay, because I don't see really from now to 2040 big changes. But you may get an information like an area that is rapidly urbanizing. Urbanization means impact on the river flow, and then you may think that there will be changes. You have to get information, okay? Other questions? Yeah, one here.
Can you make photograph an example for when we are more interested into the closed box other than the rest of the graph? When we think about the big flow, the full design flow, when are we considering the full design flow, and when we are much more interested in the lower flow in practical examples?
I would say that the question basically is when are we interested in getting a design flow that is high, and when we are instead more interested in reducing it. It depends on the type of use. I mean, if it is in use where you have to avoid oversizing because you need to save energy, like water for irrigation, if it is transferred through open channel flow, you need to really size the channels with the right flow, right design flow, because otherwise, if the channel is larger, you can't flow the water to the field. And then in this case, people try to make the design flow very low in order to make sure that when they have low flows, they can get water to the field. And for hydropower, it's different. For hydropower, people today, we have plants that are very efficient and also very flexible. So people tend to say, okay, let's try to maximize the design flow so that I can also benefit from the peaks in hydropower production, provided I have a plant that is flexible and working with good efficiency, even when it works at 10% of the design flow. It really depends on the application. Okay, I think I need to stop here now. If you have further questions, I think that we can address them on Thursday. Thank you very much.
Thank you.
Thanks to the students who attended remotely. Thanks a lot.
Thank you.